Then I might as well make a start whilst people are still slowly arriving. My name is Martin Colliver. I got sort of invited to come along to this virtual conference to, well, on the premise of computer science NEA, or computer science coursework, as maybe some of us remember it. And also, and over that time, I sort of modified it slightly and just sort of looked into how I mainly teach sixth form students now, so it looked into how we might offer opportunities for sixth form students to engage their mathematics sort of across their school in their understanding a bit more. So just in terms of a quick background, a long time ago now seems, I did a pure mathematics and computation degree, but then I initially trained as a mathematics teacher. Don't think there was a PGCE in ICT stroke computing in those days. So it was the typical route to go in as a mathematics teacher, worked as a maths teacher for a few years, moved across to computer science. I was the head of department at Warwick School for about 19 years. And just recently, just about 2-3 years ago now, moved across to the National Mathematics and Science College, which is based in Coventry. And at the same time, through those sort of many years, I've also had some quite strong links with exam boards, mainly with AQA, starting as the usual sort of exam marker, moving to team leader, principal examiner, writing some of the A-level papers. And then since 2017, been the principal moderator for the A-level coursework, what we now call the NEA. So that's my sort of little background. And so I was hunting around for a few ideas to base this on, and I'm sort of trying to think about how we integrate mathematics across other subjects. I'm a mathematician, but I'm a computer scientist at the same time, so it's quite nice to think about these sort of integrations across different subjects. And so I was digging around on the ATM's website, and this one goes back to 1995, and I think I do remember reading it at my PGCE course. Whilst I was based at Warwick University. And the key thing, just reading bits of it again, that came out to me was that sort of little paragraph there that I've highlighted. So when computer algebra systems are universal. So I remember back in 1996, 97, we were getting excited by the latest Texas calculators that could do this algebra. And so when these systems are universal, which perhaps they are now on our sort of mobile devices and things like that, sixth form mathematics classes may be able to spend more time considering the entire modelling process by solving genuine economic or scientific problems. And to me, that sort of shouted out as to what I was trying to sort of base this talk around, which is the idea that, yes, mathematics needs to be taught in the classroom, but how can we engage our mathematics students to be aware of their subject across the whole sort of spectrum of what they're doing at that moment. And I know Miles is going to talk about this, but I was just hunting around. I think it pinged up on Twitter actually today, or X as it's now known. So the Royal Society have just sort of produced their discussion paper on mathematics and data education, which I think is great. We've got a real push on data science in our college at the moment. But what stuck out to me as well while I was trying to prepare this talk was key message 5 there, which is MDE is not just a matter for mathematics teachers. And that's me, because I'm not a mathematics teacher. I'm now a computer science teacher. But this idea of mathematics and data education, which does involve computer science quite heavily, does involve other people apart from mathematics teachers. So I think that's quite a key message there. And therefore, there are other teachers for us to try and engage in terms of being aware of what mathematics can do for them. And so I'm going to talk about 3 different areas. I'm going to talk about the computer science A-level. I'm going to talk about EPQs. And then I'm going to talk about an initiative that we started at our college, which is called the STEM Communication Project. And so I'm going to sort of rotate around those 3 ideas, trying to show different ways that students who have a capability with mathematics, they're doing it at A-level, can use their mathematical skills across other subjects. And so let me start off with the one that I've got most exposure to, which is the computer science NEA. And so in 2017, when we were sitting together trying to build the new specification, we wanted to move away from the sort of not a problem, but the situation that we had arrived in, which was basically everyone was doing databasey projects, and the mark scheme was sort of tailored towards those. And we also wanted, so this is AQA, we also wanted to allocate more marks to the programming, the skill side. And so we adjusted it so that the 75 marks, 42 of them now definitely come from the implementation of their project. And the way the spec was then written up in 2017 allowed, well, we hoped would allow for a greater opportunity for different kinds of projects, and also a greater opportunity for different environments. So and a move away from Microsoft Access and Visual Basic, hopefully. And it has worked. So in having moderated hundreds of projects recently, there is a clear movement away from just simple Microsoft Access and Visual Basic projects, which we were seeing a lot of a few years ago. And so what it does allow us to do is to think about, well, how can mathematics come into the computer science? And I expect not all, because I've had students in my past where they've done computer science and haven't done maths. So they've done computers. I had one student do computer science, music, and something else. And actually, the way he programmed was really interesting. He really saw programming as something creative, maybe not so mathematical, but definitely saw it in a different way. And he really came up with a nice project. That was a while ago. So don't have to be mathematicians. But I would suggest that the majority of computer science A-level students are probably doing mathematics. So where can that take them in terms of projects, and how can they use their mathematical language, their mathematical skills to help out in their projects? And so I was just reflecting back on some of the projects that I'd seen in 2023 with what I regarded a larger amount of mathematics than perhaps other skills. And we're seeing sort of more of these projects turn up each year. Saw quite a nice lot of graphical calculators developed by the student. And that might be out of interest of, they've got a graphical calculator in front of them. And so therefore they sort of think, well, how can I actually do this myself? And that leads them down into some nice sort of tasks for them to perform, even if it's just the sort of the tokenization of an expression, so it can then be evaluated, some nice sort of skills. We see a lot of simulations now across our projects. I think for the first time this year, I've actually seen some students try some fluid dynamic sort of projects where they were trying to show sort of air movement around things and around obstacles. So this is fluids around obstacles, which is quite nice. Use of finite element methods to sort of simulate smaller parts. Continue to see quite a lot of predator-prey simulators, and then students linking it back to some of the equations that can fit around those. Since COVID, we've seen quite a lot of people looking at disease spread and the modeling of those sort of things. We often get solar system simulations or particle simulations, and sort of the physics. And I suppose that links into A-level physics as well. So actually, you then get a student who's managing to link computer science, physics, and maths together all in one, which can actually be really useful for them when they're doing those subjects, because it brings it all together and helps reinforce things, which hopefully is maybe what we're aiming for as teachers, to engage students with learning rather than just individual subjects. Games can bring in a lot of opportunities. So we see Perlin noise. I had to look up what the student had done, but they'd done ant colony optimization, which is a sort of a way of learning, machine learning. So I had to go away and sort of Wikipedia that myself before reading what the student had actually done with it. We often see students attempt machine learning, genetic algorithms, neural networks. And that's interesting. I think that does heavily imply that when the computer science spec is updated in the future, if A levels continue, I think AI is a topic that's not really on our spec at the moment, which needs to come in, because there are a lot of students interested in it. There's a lot of resources trying to get us to engage with machine learning. It's important in terms of just what's going on in the world around us at the moment with things like ChatGPT and Copilot. So that's a big topic that students have a play around with, and the maths behind it again is quite interesting for them to look at. It links it sort of links the ideas that they might be seeing in the maths lessons to something actually quite physical that can do something. One of my best students from a few years ago looked at building it's just a Tetris game, so a nice Tetris game that he built, but then attached a genetic algorithm to learn how to play it. It was really good, actually. So after a few hours of training, it was really good. So at the end of the year, we gave him an award saying that his project might become sentient sometime, because it was actually learning quite a lot. But it was really good at Tetris. 3D terrain generation, because the maths behind that is quite heavy and deep. You can see an image there from a 3D terrain generator that one of my students produced last year. People looking into probabilistic things, so spam filters and other things that have to do with sort of that kind of area of mathematics. An interesting one I'll show you on the next couple of slides, a student attempting to do their own raster graphics drawing program. So sort of taking shapes, but then thinking about, well, how do we draw them if all we've got is small pixels? And it's a really interesting project. I've got some nice images from it because it's really quite nice to look at. So here on the left, you have a student who's just built a graphic calculator, and you might sort of say why, but in some ways the learning behind it is quite nice for the student. So it's plotting a line. They can change the line, they can find the roots, they can do other things with the line. I think the calculator then actually allowed multiple lines, and it allowed to find where points meet and things like that, and it was really quite powerful. But then below that, it also offered the opportunity to do differentiation as well. And when a student starts trying to work in that in computer science, they sort of have to do that battle of how do I break down a mathematical expression into tokens that then can be used. And we see a real difference between the student who does understand maths and the student who maybe doesn't. The student who makes a quiz that perhaps doesn't understand that 2 + x is the same as x + 2, because they don't write the system to be that flexible. And then the student who does understand that mathematics is quite flexible and is a language that needs to be understood, begins to realize that actually I need to look at this expression, I need to be careful, I need to break it down, I need to understand what's going on. And it can be quite powerful, it can be quite learning. The one on the right is the student who is looking at a spam filter. This is in their early part of the project, where they're considering different ways that they could have solve this. They went for the probabilistic way in the middle eventually, and just wrote a sort of a spam filter system, which was quite nice. I was reading this one again this morning, trying to find some examples for you, and I liked it, so I just thought I'd put a few in from this. This was the raster graphics one. When I was reading through it again, I was reading how much the student was actually playing around with mathematics to get it to do stuff. And so there's how we can do lighting. There's just how we draw polygons, how we can use the maths to help us draw polygons. There was a nice algorithm for actually drawing a circle onto the screen, because obviously you've got to break it down into pixels, and pixels are squares. So how do we draw a circle? It becomes quite complex. And then lovely things like filters that you can put onto images. Now, filters are just basically mathematical expressions. And so we've got Gaussian blur, we've got other blurs. I actually like the little teddies that they used in the project to sort of show what their code could then do. And so different kinds of manipulation of that image, just using, because if an image is just pixels and a pixel is just numbers, then what do we do to that? Well, we do maths to it, and it's just really quite nice. Rotating the teddy bear. And then the sudden realization from the student that if we pick up the pixel and rotate it, we get little gaps. And so then the student looked into smoothing and things like that. The bottom paragraph from the student talks about actually how they sort of came up with their own DIY solution, which was just to sort of do an averaging system around groups of pixels to fill in the gaps. But it actually looks quite nice. So they've managed to take that teddy bear and rotate it, but just do it themselves mathematically. So they've written the code. Yes, I know I can do it in Paint, I can turn a picture around, but they've worked out the maths necessary to do it. And then that's the second page is just testing from their project. And so you've got all these lovely effects that this student has actually begun to realize that they can do by using maths on an image. And so we've got mosaics, and we've got half tone, and we've got rotates, and it was lovely. It was a high scoring project, but sort of shows you the kind of things that maths can be involved in with a computer science project. If you think, and sound is another one as well, because again, if sound is just samples of music, well, then we can use maths to manipulate those sounds. And there can be a real engagement between something not physical, but something you can see, like that teddy bear, and then the maths behind it to actually manipulate it, which I think is quite fascinating. Okay, so lots of opportunities, but they might not be doing computer science, but definitely lots of opportunities to bring maths into the computer science. And we can talk about functional programming a little bit at the end, because the AQA spec also does have functional programming. But then as I was beginning to think about this, it's just not computer science where mathematics can actually be involved. So having worked with the EPQ for a long time at Warwick, and then just recently at my new college, again, maths can come into this. I haven't got too much about this, but I found this from the sort of Centre for Public Engagement, but it links back to probably those first few slides about trying to grasp mathematics students. And so they're sort of saying, for pupils studying mathematics at A-level, it's not always clear how techniques they acquire can be applied to solving real-world problems, which is, again, sort of like the computer science NEA. How do I take these maths and manipulate an image? There's little opportunity to explore the skills involved in creating and solving a mathematical model. Pupils are left with a toolbox of methods and with no sense of how they should use these. The EPQ provides an ideal opportunity to explore mathematical modelling, maybe going back to that Royal Society paper that talks about data exploration. So trying to realise that an EPQ can be another avenue to engage students with the maths that they know, but then applying it to something outside of their maths classroom, which I think is fascinating. And so just to dig around of some previous titles that I've been aware of and seen. Some of these are more mathematical than others. An equation for beauty. Yep, okay. Fractals and their capabilities. Fractals are nice. Just some sort of discussion, E or pi. Football predictors, again, if they're not doing an EPQ on it, that could be a computer science project. I often see, we saw a few football predictors this year. So they would take the statistics from last year and they would try and use that as a model to help predict how clubs would do this year. But again, it could be an EPQ. So there's a real opportunity there for a student, if you've got a student in your class who's doing well at maths or further maths, and you could do an EPQ on this. And there's also the sort of reminder that an EPQ does not have to be just a 5,000 word essay. You can build an artifact and then write up a much shorter essay. And so the artifact could be a simulation, or the artifact could be a data analysis model. So they could go away and look at a large set of data. They could build a model of analysis around that data, and then they could then use that and then write a sort of a summary around it and their conclusions. So there is that opportunity. Quite a lot of schools still sort of look at the EPQ. It's quite a nice opportunity for a scientific and mathematical student to apply their skills in a different way, because they're having to build something and then write about it as well. So maybe it engages them in a slightly different way. Okay, so integrating across subjects became important for me, but then also important for our college at the same time. I was looking at how we can link together all of our sort of STEM subjects at our college. We got Teacher Research Network from Warwick University sort of got behind us as well. But then out from this came what we're now calling our STEM Communication Project, which is basically trying to encourage all our students not just to study their subjects, but to sort of live their subjects and to be able to be confident about talking about their subjects. And so as a college, we took a step back and we said, oh, how do we build confident students who can use, well, all of their skills, but specifically their mathematical skills, their analysis skills, and be able to present their work appropriately. So for the last, well, it launched last year. It's now into its second year, but it's called our STEM Communication Project. And again, it's perhaps another way thinking about how do we engage our mathematicians outside of the classroom. So our STEM Communication Project is trying to encourage them to think about what does it mean to do academic research and public engagement. So what does that next, what's that next thing look like after their A-levels? As a college with quite a lot of international students as well, we're always trying to build up English communication skills, but I think that's useful for any A-level subject or any sort of 16 to 18-year-old to build up communication skills. How do we engage with other people who like STEM? This is an opportunity to provide challenge outside of lessons. So again, that engagement outside of our maths or computer science classroom to carry on with our subject. Produce content in line with our standard as trying to be sort of a beacon for STEM, but also for the college to establish partnerships with academics and professionals, the usual sort of things that schools and colleges want to do, these sort of linkages. The purpose behind it is to make sure that every student goes through a sort of a series of steps. So across their time with us, they will do they start off with a paired research project, but they end up with an individual research project. We introduce skills that they might need in academia. That they're introduced to the idea of a poster presentation. They're introduced to the idea of a viva. They're introduced to the idea of a peer review. The sort of things that they might be exposed to later. And to help us on that journey, we bring in people, academics, to sort of come and talk to our students about the research that they're doing, to sort of try and inspire them, to show them what is going on at universities, but also to talk to them about what it means to do research outside of just your normal lesson time. So you can see a few of the people that we had over last year. We've also got a mathematician in residence now. So Katie is spending time with our college across this academic year. And she pops in and does things with us. And so that's quite a sort of nice sort of feature to have as well. Or a scientist in residence. I know other schools have artists in residence and, things like that, musicians in residence. We decided it'd be quite nice to have a mathematician in residence. And so what does it look like? Well, we only did it last year. And so I just wanted to just quickly show you some of the posters that are, so these are what we would call our year 1 students. So this is National Curriculum Year 12, first year of A-level. And so these are actually, Misha and Mark are 2 computer scientists. They wanted to analyze different ways of calculating pi, which is, a nice standard thing to look at. There are many different ways that we can calculate pi, but it's an interesting challenge for them to have a go away and have a look at, and then to try and write up themselves. And it brings together quite a lot of ideas. For me, it brings in the computer science. For the mathematicians, it brings in some nice algorithms for looking at different ways that we can do pi. And it just brings in this idea of communication, because they're having to try and build a poster around it to present their ideas. I just zoom into one bit because there's maths. And so it's quite nice just to sort of here today with you, just to sort of say these are students who are grappling with some nice maths, but then actually sort of writing it up as a poster. So this is not just solving mathematical exercises. This is actually trying to go away and present something. I didn't zoom into the one on the left actually, but that's their, I think that's their Python code. And they also looked at the Monte Carlo algorithm as well, which was just nice to see them looking at different ways of doing it. And they compared and contrasted, so you can see their results. And then they came up with a little conclusion at the end as to which method they thought was best for calculating pi. Someone else did it as well. It became quite a popular across a few of the students. And again, you can see they've gone through a similar sort of task. But they've gone through this as what you might call an academic study, and they have managed to present a poster which we were quite proud of at the end of our first year. doesn't just have to link in. So as a STEM subject, we've got quite a strong biology department. What with there being a lot of open data around at the moment about COVID and things like this, I'm not sure about the real linkage between this. But then, if students come up with an idea of a question they want to answer, and they go down that route, and then that's fine. It's a journey that they're going through. But we found a massive load of data about COVID-19, but we also found data about the temperature of those particular areas. So we had like area data for COVID, and we had temperature data for that particular area across the many different places across the world. It's a massive data set. And so they sort of said, well, I'm going to analyze whether there's an impact of temperature on the transmission of the virus. But they did it as a little research project, and they came up with their conclusions. And to me, in the middle, there is the sort of the maths and the data and the Python. And so that's, to me, that was quite interesting. Thank you, Miles. Yes, that's the lovely thing about data, I think, sometimes, is that it shows, it's alive, and we can pull different things out of it, and you can sometimes come up with sort of really strange conclusions that perhaps probably don't make sense, but the students going down the journey of actually having a real go. You just see what else. And then this is a really bizarre one. So we've put them all up around our college because they look quite nice as well. And so I suddenly spotted this one as well. Factors affecting the flying time of a helicopter. Where that idea has just sort of come out from somewhere. And I think they made little paper helicopters. But there's some nice complex maths there. And they've managed to sort of link it in with an experiment. And they've managed to then present it on a poster, and they've sort of come up with their own conclusions. And to me, that's fascinating. If we can get 16, 17, 18-year-olds having a real good go at that, and if it doesn't quite work, and if their results are a bit spurious, and then if we start probing a bit deeper, and sometimes we find mistakes in their methodology or the way they're thinking about it, it's a learning journey for all of us. But for the student, it sort of really helps them build up those skills. There was our poster event, to which we invited students and local academics, and obviously a group of other people. And it was a really nice sort of event where, again, the students were asked to discuss their results and their posters. And actually, the majority of them could talk very well about what they had written up. So, yeah, it was fascinating. Linking it back into some of the ideas of this strand, which is considering functional programming, which I'm seeing more and more of across my computer science students. We're beginning to see glimmers and bits of it in the computer science NEA. We talked quite a lot today at some of the other sessions about Haskell. Haskell is our pure functional programming language, but you can throw in functional features into C# and Python, and that's perhaps where, as a computer science teacher, I'm seeing more students sort of dabble with it. I think it'd be quite rare to do a whole project in Haskell at the moment. Might do eventually. I've got an example of one in a minute, but that was written by someone who wanted to show it as an example. Oh no, so it's not Haskell, it's still C#, but we are seeing them in sort of beginning to see glimmers inside C# and Python. And to me, that's exciting. I think it's an opportunity to keep developing. I think it links quite nicely into the maths and some of the ideas I've heard from some of the other talks. So I met this, he's a retired teacher now. He's a retired software developer, really. Met this Richard Pawson because he started a job at sort of well, quite a prestigious school where he's helping out their computer science department. But as he was doing this, he's asked AQA and us particularly, he keeps challenging us to sort of think about where we go next, and it's really quite interesting talking to Richard. He produces resources. He's produced sort of programming introduction books, but specifically for maths and science students, and he bases it heavily along the ideas of teaching functions first. You'll see a lot of his blogs and threads on sort of compute and teacher forums, where he's a real enthusiast for sort of a functional way of thinking, which is great just to have those ideas floating around. So he's also written a lovely resource about functional programming in Haskell and C#, which is quite nice. He really likes old school code as well. So he's written a lovely resource, because for the A level, we have to do assembly programming. So he's written a whole resource about building Snake and assembly code, which again, just, he's an exceptional person. But he wanted to take on the challenge, as you do. He wanted to take on the challenge to show that you can actually write quite a short computer science coursework, because historically sometimes these are quite long, and they don't have to be. It's just a sort of a problem that the computer science coursework has got into. And so I think sometimes teachers and centres are a bit frightened if the coursework is not greater than 200 pages long, and it doesn't have to be. I'm a real proponent for giving examples of shorter projects, and some of these mathematical ones we've looked at early are shorter projects, because the skills are the complex maths. And so therefore it's not a database project, and we don't need streams and streams and streams of tables and images showing that, I can add a customer, I can add an order, etc., etc. We just need to test the maths. So he decided he wanted to do a totally functional one. So he wrote a Wordle server. I see quite a lot of Wordle servers to do all sorts of puzzle things across the year. But Wordle Solver is quite nice because it's quite up to date. But he wanted to show how a short project could get. He asked me to then give a guidance mark for it. I don't think it was quite full marks, but it was pretty close. But the code on the left, ignore the sort of find out live function in the middle. I'll come back to that in a second. But the code on the left, this is on his website if you want to go and look for it. Is just a page of code, and we're quite used to students having to present, humongous amount of code that perhaps doesn't do particularly much. And he wanted to demonstrate that if you use functional programming and functional ideas, you can write a Wordle server, and it's a page of code. There is further code that's full of words, dictionaries, basically. And this very cleverly does solve Wordles, and it solves them very well, actually. He uses a very mathematical and functional way about thinking about, okay, so what guess should I do first? And then depending on what's marked green and yellow, what guess should I do next? And he just uses a very mathematical way of considering it. And it's really quite elegant, and it's quite nice. And I can't remember, I think it always solves it somewhere between 3 and 4 guesses from memory. But it's worth going to look at his website and reading around it. But he wanted to do this because I think the whole project is about 50 pages long, and it's just really nice. It just shows that students can think in a slightly different way to get the high marks. So Haskell is a lovely language, and we do have to teach it for A-level computer science. But I'm beginning to see, even as I teach Haskell, I'm beginning to see students take some of those ideas and bring them back into Python for me. So the code there is definitely at what we would call advanced A-level standard. But I'm beginning to see more functional ideas in my weekly Python challenges. So rather than just using sort of iterative loops and things like that, sometimes they're being a little bit clever. Might not call this truly functional, but we have a student there who's actually using is realizing that if we want to solve the problem I set last week, we can just do a filter on the list, which perhaps is a functional way of thinking. So I'm just going to put a filter onto this list, and then he's used an anonymous function to actually then do the filter, which is quite nice. And so these skills are beginning to percolate around, which is quite nice to see. Aha, oh look, that 236, that's it. So what I've tried to do is just sort of try and show you glimmers as to, where these mathematical skills can actually get embedded for a sixth form student. I'm aware that, this can't happen everywhere, but there are ways that you can talk to a mathematics student, and you can sort of say, well, are you doing computer science? Or because sometimes the student doesn't know what to do for their computer science coursework. So there are opportunities to sort of actually, you could base it around this, or how about taking this further? So I've just tried to give you some glimmers about A-level computer science coursework, NEA, the EPQ projects that students might be doing, and they might suddenly think that, oh, I can't do that on maths, but actually you could do it on maths if you came up with something nice. And then what we call our STEM communication project, which is, again, just trying to engage students with their subjects, but outside of their subjects, get them talking about their subjects, exploring their subjects. So I hope that was of interest. There is any questions slide. So I will just take us back. I'll stop sharing and I'll just see if anybody's got any questions or anything they want to say about that. Let me just bring up my chat. Okay, so yeah, what's the kind of structure we use for the STEM communication project is that we allocate students, so they get one lesson a week for it, which is sort of an hour. But they get that for every year that they're with us. We do take students in for what we call a pre-A-level year. Not all students come for that, but some do. So it's sort of like a bridging year between GCSE and A-level. But then year 1, year 2, again, they get one lesson a week. So that's an hour a week. But interestingly, that they do seem to engage with it, and they do seem to then get excited about doing sort of more work on it. That might just be we're lucky with our kind of students who are passionate about we are a STEM college. We have 150 students now who are just studying STEM subjects. We have problem boards around the college. They're used to solving those at any time. So we are trying to engage them in their subjects outside of lesson time. But they get one lesson a week.
You mentioned that they typeset their projects in LaTeX.
Mm-hmm.
Do you devote time to teaching them how to do that?
Yeah, so they sort of, in the first year, they rotate round a variety of skills. So they get data science skills where where my computer science colleague teaches them about pandas, seaborn, and those kinds of skills. And we work through, actually, we go through some of the A-level large data sets. So we work through those. There's a nice NEA resource that helps you do that. So we tend to use that one. They get sort of literature view, but then they also get the skills for typesetting as well. Now, they don't have to do their poster, but I think we're trying to encourage them to write up their sort of short article using those kind of skills.
Would you consider Jupyter Notebooks as a means of deployment? Yeah,
we're looking more into that. And actually, fascinating. I think I noticed it last year, but I'm using it more this year. I can actually set my coding assignments now in Teams using notebooks, which is brilliant. So I can put up, I can do Markdown, I can do little Python cells, and then I can push that out to my students to complete as work. And it works really well. And so something that Microsoft have done well. I can actually push Python into Teams.
Yeah. Good.
Yes, I like that comment in the chat. There are definitely different ways of solving things. Yes, I have got some really good programmers in my upper sixth year 2 at the moment. And sometimes, like the example I showed you a second ago, sometimes they're answering A-level questions in a way that I am slightly concerned that examiners won't be able to mark, which is an interesting place to be. Now, I'm in a fortunate position that I know the examiner who writes the programming paper. So every so often I send little snippets of answers across and sort of say, well, what mark would have this got on this past paper? And the comment that always comes back was, well, it works and it should get full marks, but would a normal examiner be able to spot that? Because the mark scheme is structured in a very iterative way. So even if you use a list generator, which might be quite common in Python, but the mark scheme will talk about, having an iterative loop and then working your way through the list, and it will be, the mark scheme will be structured in a sort of very sort of standard way of solving the problem. But if they suddenly, I mean, going back to that previous example, if they use a filter with a lambda function, you've got to have an examiner who actually then can look at that and actually understand it. But hopefully, with Haskell and functional programming being on the spec, the teachers, the examiners will be moving in that direction. But you're right. There are efficient ways, there are elegant ways, and there are ways that maybe examiners can't mark yet. And we have to sort of be aware of that. But it's all a learning journey for all of us, hopefully.
So I think you alluded earlier to the Advanced British Standard and the reform of 16 to 19 qualification space. Do you have any feel for what happens to non-exam assessment in that?
No, not yet. It'd be great if they could keep something like that in, wouldn't it?
It really would.
It could somehow give opportunity for a student. Yeah, it's sort of like the STEM, it would be like our STEM communication project then, wouldn't it? So that
and as you've been talking this afternoon, I've been wondering, why do we not have an NEA in A-level mathematics? You have such fabulous work coming from your students,
Yeah.
It's great that they're doing this in Pooting, but what about maths?
Well, well, this is that's it's meant to be a whole thing across our college. So that there's biological projects, but a lot of them do obviously have data analysis underneath them, which is really nice. I think data science is one of the key uses for our maths at the moment. So I think the more that students realize that they can grapple and engage with that, it's really quite useful for them. Okay, well, I think we've got to 2:45. So thank you very much for joining me.
Thank you
very much, Martin.
Thank you, Ian, for inviting me along.
Will you